First of all, I would like to thank the organizers for inviting me to this conference. I am really pleased to be present at this exciting meeting, and it is my great pleasure to have the opportunity of giving a talk to you. Today, I'm going to talk about our recent progress in electron momentum spectroscopy, EMS. The topics here involves the first attempt to extend the measurement from the static to the time-resolved regime. It is my purpose to show you this new time-resolved spectroscopy, as well as accumulated knowledge of many years of EMS, might be able to provide new dreams which may come true in the near future. In addition, you will see how lucky I am to be with excellent colleagues whom I have had the greatest pleasure of working with. Well, to begin with, let me remind you about the basic physics of electron collisions. An atom or molecule may be raised from an initial state to another state of higher electronic energy in a collision with an electron having sufficiently high kinetic energy. The resulting inelastically scattered electron having a lower kinetic energy emerges traveling in a direction. The time-independent probability for the occurrence of such a particular collision process is usually given by the Bethe volume formula. Here, E and K are the energy and momentum transferred to the target atom or molecule from the incident electron. dF over d is a quantity called the generalized oscillator strength, and it can be put on an absolute scale by using the Bethe sum rule. Here we have an example of the Bethe surface, which plots the generalized oscillator strings of helium as a function of energy loss and momentum transfer. At small momentum transfer or in a full scattering directions of the electron projectile, we have the dipole regime in which excitation of the target is very similar to photoabsorption because the momentum transfer vector and the electric vector play the same role in this case. As the momentum transfer increases, you can see the continuum part of the spectrum moves toward higher energy loss. The diagonal ridge running through the Bethe surface is called the Bethe ridge, and its high energy limit is known as Compton scattering. Electron momentum spectroscopy, EMS, that we will discuss here is an experimental method based on such electron Compton scattering. The method involves coincident detection of the two outgoing electrons produced by electron impact ionization. It is therefore possible with the aid of conservation of energy to specify the ionized orbital from which the target electron is ejected. Similarly, from conservation of linear momentum, recoil momentum of the residual ion can be determined. If the experiment is performed under the electron Compton scattering conditions, where collision kinematics most nearly correspond to a collision of two free electrons, with the residual ion acting as a spectator, the momentum of the target electron before ionization, P, is equal in magnitude, but opposite in sign to the ion recoil momentum, Q. In this way, this method enables one to separately measure Compton profiles associated with each target electron at different energy levels, or to look at electron orbitals in momentum space. This is a schematic picture of the latest version of our EMS spectrometers. We use the symmetric non-coplanar geometry in which magnitude of the target electron momentum can be determined only from the out-of-plane azimuthal angle difference between the two outgoing electrons detected. The idea here is to achieve the desired instrumental sensitivity by covering almost completely the available azimuthal angle range for the symmetric knockout planar E2 reaction. Briefly, electron impact ionization occurs where instant electron beam of 1 kilo electron volt or higher collides with gaseous target from 8 gas nodules. 2 outgoing electrons emerging at the scattering angles of 45 degrees are dispersed by a spherical analyzer and then detected with one large area position-sensitive detectors. Since the spherical analyzer maintains the azimuthal angles of the 2 outgoing electrons, both energies and angles can be determined from their arrival positions at the detectors. This technical progress in instrumental sensitivity allowed us to make in-depth analysis of resulting high statistics EMS data, such as for density oscillation and vibrational effect on the electromomentum densities. This technical progress has also encouraged us to develop an advanced form of EMS, which is called time-resolved EMS. These 3 topics that I want to discuss with you today. Let me begin with the topic of density oscillation. Density oscillation is a phenomenon particular to momentum space wave functions. For instance, in the case of the hydrogen molecule, the wave function can be represented by a linear combination of atomic orbitals. And we see in momentum space the position information about the equilibrium nuclear position is present only in phase factors that are introduced by a Dirac-Fourier transform. Our point here is while the experiment usually suffers from spherical aberration due to random orientation of gaseous target molecules, cosinoidal or sinusoidal modulations still survive in the measured spherically aberrate electromomentum densities or electromomentum profiles. Therefore, one may have a chance to get information about not only molecular geometry, but also spatial orientations and phases of the constituent atomic orbitals. As a showcase example, I present a result of the first observation of density oscillation obtained for the CF molecule. These are experimental electromomentum profiles measured for the 3 outermost orbitals of the molecule, each of which is represented by a linear combination of the fluorine 2p atomic orbitals. In order to make density oscillation directly visible, we divide the experiment by the associated theoretical cross-section for the isolated fluorine 2p atomic orbital. Then we see each orbital has its own oscillatory structure. Furthermore, the interference factor for these 3 orbitals can be represented in this form. So the intensity at the momentum origin is directly related to the spatial pattern of the molecular orbital. For instance, the intensity value of 12 at the for the 42 orbital immediately tells us that the constituent fluorine 2p atomic orbitals are completely oriented in the same direction. The same conclusion can be reached also from comparison of experiment with the allowable oscillatory structure for each symmetry-adapted molecular orbital basis. We are now conducting similar measurement for various molecules to have a better understanding of density oscillation. One of an example for this is the result for the hydrogen molecule. You can see the expected curve shown by red line is rather different from a structure created by using the isolated hydrogen 1s atomic orbital, and is consistent only when a spatially constructed atomic orbital is used in the analysis. They're supporting chemical bonding theory in that shrinkage of the hydrogen 1s atomic orbitals occurs upon molecular formation. I would note this topic may be related to that excellent work of next speaker. Now I turn to the second topic, vibrational effect on the electron momentum densities. Influence of nuclear motion on the electron property and dynamics is known to be very important for many physical and chemical processes. For instance, electric dipole forbidden transition often appear in optical spectra, and this is explained by vibronic coupling that involves the interaction between electronic and nuclear motions. To put it simply, a molecular orbital at the equilibrium geometry may be deformed due to molecular vibrations so that its electronic transition character is changed. Such vibrational effect on the electron momentum density can now be clearly observed with EMS. As a showcase example, I present the result for the ethylene molecule. This is the experimental momentum profile observed for the 1b3g orbital of the molecule. You can see while the experiment shows substantial intensity at the momentum origin, the theoretical calculation at the equilibrium geometry predict zero intensity. This is because the intensity at the momentum origin is a measure of the balance between the positive and negative phase areas of molecular orbital wave functions, and hence only totally symmetric orbitals can have non-zero intensity. The observed difference between experimental theory is due to effect of molecular vibrations. Within the harmonic oscillator approximation, we have found influence of molecular vibrations on the electron momentum densities can be written in this form. Here, the second term is responsible for vibrational effect. And the theoretical calculations with vibrational effect clearly reproduces well the experiment. So deformation of orbital due to molecular vibrations is thus identified. Now we are conducting similar measurement and calculations for various molecules to have a better understanding. Systematically, I investigate vibrational effect on the electron momentum densities, some of which are running as a joint studies with Professor Duluth and Dr. Molini at Hasselt University in Belgium, who have developed a different theoretical approach that employs molecular dynamics simulation on the Born-Oppenheimer potential energy surface. If you could have an interest on this topic, please visit our posters that Dr. Molini at Hasselt University and Dr. Watanabe at my group put up on Friday and Monday. Now I turn to the moving on to the last topic, development of time-resolved EMS. As you may know, EMS experiments have a long history since early 1970s. Nevertheless, application of EMS has long been limited to stable target in their ground state, except the early pioneering work of Professor Weigald at Flinders University in Australia on excited sodium atoms prepared by using a C-double link dye laser. In order to make a breakthrough in this limitation, in 2008, we began an attempt to develop time-resolved EMS. Although the data quality is currently low, I would like to report to you our continued progress. Time-resolved EMS is an experimental technique that employs ultra-short laser and electron pulses in a pump-and probe scheme. Ultra-short laser pulse is used to excite a molecule, target molecule. Then the system is allowed to evolve for a period of time during which the transient species decays, such as electronic relaxation, isomerization, and dissociation. Then after a certain evolution time, the transient species is proved by EMS using ultra-short pulsed instant electron beam. This is the experimental setup of time-resolved EMS. Briefly, the 800 nanometer output of a femtosecond laser is split into pump paths and electron generation paths. 90% of the output is used to yield the pump laser pulse, which excites a molecule in target gas beam after the 5 kilohertz repetition rate being halved. On the other hand, 10% of the output is frequency tripled to produce electron pulses by a photoelectric effect. The photocathode is made of a thin silver film, which is negatively biased to accelerate electron pulses up to 1200 electron volt. The resulting electron pulses of 1 picosecond temporal width is used to induce EMS scattering. The resulting EMS events are detected by an EMS spectrometer, for which an exceptionally large spherical analyzer is employed. As a showcase example, I present first result of a relatively long-lived molecular excited state obtained for the toluene molecule in the first excited singlet state. This state can be created by 267 nanometer light through the pi star excitation transition. This is a comparison of binding energy spectrum, EMS binding energy spectrum, from the molecular excited state with the traditional EMS data from the ground state toluene molecule. You can see these spectra are substantially different from each other. This is due to the difference in the initial state electron configuration. To make it concretely, let us consider this electron configuration for simplicity. Both the ionization from the initial ground state are allowed because these are one electron process. On the other hand, this transition from the initial excited state is forbidden because this requires simultaneous excitation of 2 electrons. Results of an analysis of this kind are involved in this figure, which has been generated by the symmetry-adapted cluster configuration introduction method. The vertical bars indicate pole strings. That is a probability of finding one-hole configuration in the final ion state. From the good agreement between experimental theory, it is found that EMS from an initial excited state is a sensitive proof for one-particle, two-hole configurations, those involving pi star excitation in this case. If you could have an interest on this topic, please visit our posters that Dr. Yamazaki at my group put up on Monday. As another showcase example, I present results of a short-lived molecular excited state obtained for the deuterated acetone molecule with a lifetime of 13.5 seconds. This is the experimental momentum profile measured for the outermost 3s Lindbergh orbital of the molecular excited state. Also included in the figure is the associated theoretical calculation generated by using the density function theory. In addition, theoretical momentum profile for the outermost orbital of the ground state acetone is included as a reference to highlight the behavior of the 3s Lindbergh electron. Although the statistics leaves much to be desired, you can see the experiment shows a maximum at the momentum origin, and its intensity drops off with an increase in electron momentum. This can be understood by considering the nature of the 3s Lindbergh orbital in momentum space. Generally speaking, the angular part of a wave function is unchanged, invariant under the Fourier transform. So a molecular orbital in position space has a similar shape in momentum space. On the other hand, the angular part of a wave function is largely affected by the Fourier transformation. High density at large L lead to high density at small p and vice versa. Therefore, the diffuse 3s Lindbergh orbital possesses the sharply peaked momentum distribution. The associated theoretical calculation support this observation. We have had a good luck to have carried out this work in the following 3 points. Firstly, we got eventually the signal somehow. Secondly, you may be feeling hopeless with the poor quality data, but we are not, because we are optimistic enough to move forward. Thirdly, we have taken a great deal of encouragement from the American Physical Society and the Nature magazine. For instance, the latter of which has reported this work such that a technique could pave the way for imaging electron behavior as chemical reactions happen. This is true, as it is electrons that bind atoms into molecules, and the chemical reactions are all about the rearrangement of these electrons. Our future direction is, of course, to go towards the challenge that is to take a snapshot of molecular orbitals changing rapidly, such as during chemical reaction. To that end, however, we have to improve the apparatus and the technique substantially, mainly in terms of signal to background ratio and time resolution. The signal-to-background ratio is limited by space charge effect in the incident electron beam intensity. And the current time resolution of 35 picoseconds is governed by the velocity mismatch effect that originates in propagation speed difference between the light and electron pulses employed. These are really, really awkward problems. So any of your comments and suggestions are important to us and highly appreciated. Finally, let me summarize my talk. We have employed the multi-channel advantage of an EMS spectrometer in two ways. One is to make in-depth analysis of high statistics EMS data for density oscillation and the vibrational effect on the electromomentum densities. We expect a more complete understanding of momentum space chemistry will be achieved, which could be useful for various fields of research. The second is to develop time-resolved EMS. The work on the acetone molecule have represented the first time that measurement of electromomentum density for short-lived molecular excited states are feasible, opening the door to time-resolved orbital imaging in momentum space. We believe by improving the apparatus and the technique step by step, one will be able, hopefully in the near future, to film molecular orbital movies, thereby making it possible to access the driving force behind the chemical reactions. Thank you very much indeed for your kind attention and patience.